Let's get started. We have a lot to cover and only about 25 minutes to do it because you got a quiz today. But you're going to be ready. I want to do a very brief review. I want to do some practice problems because that's on the syllabus for today. And there's a couple things on the homework that I haven't finished covering yet. So I want to talk about those today. Make sure you know how to do them. You have all the tools at your disposal now. I have given you all the tools you need, but you don't know how to use them yet. So I want to make sure that you do know how to use them. In review, some of the terms that we have talked about during this section of the class. We talked about electric potential energy. It's measured in joules. We said that the electric potential energy, you can calculate it using that equation down there at the bottom. K equals QQ over R. That's for two charges that you bring close together. But it's not the most useful thing that we have learned. So we said, what can make it more useful? We could generalize it, like what we did for electric fields. We did forces, that was very specific. Electric fields are more general. We can divide out that charge, and we can get the electrical potential energy per unit charge. Electric potential energy is measured in joules. Electric potential energy per unit charge is measured in volts. That's why we call it voltage. So the voltage, also known as the electric potential, measured in volts, right? That's the unit. That's joules per coulomb. Can be calculated with KQ over R for a point charge. We talked about equipotential lines. Equipotential lines are lines that represent an equal amount of potential all along that line. If you walk along that line, your potential doesn't change. If you go from one line to the next line, your potential changes a fixed amount. If you go two lines, then your potential changes twice that amount. Equipotential lines are just kind of like a map of potentials in space. We talked about capacitance and capacitors, and we spent this whole week talking about capacitors. Capacitors are devices that store up charge. How good they are at being a capacitor is determined by the capacitance. That's this C. What is capacitance measured in? Farads. Yep, farads. 1 farad is 1 coulomb per volt. Coulombs divided by volts is farads, because capacitance is charge divided by voltage. The charge on the plates of the capacitor divided by the voltage across the plates. That is right here. It's the unit for capacitance. Oh, right here. 1 farad is 1 coulomb per volt. Yep, if you look at the equation, you can figure out the units. Yep.
Okay, sorry.
If you look at the units, you can figure out the equation. That's a useful tool. One of those epiphany moments I had as a physics student was that I didn't know an equation, but I did know the units, and I looked at the units in the problem, and I just solved the problem using the units. I'm like, wow, I'm like a superhero. It's like a wizard.
Crazy how math works.
I love it when math works. Math is it's so fun. People get scared by it. That's also true. We talked about dielectrics and how dielectrics, if you add a dielectric to the middle of a capacitor, it's an insulating material. And if you add a dielectric to a capacitor, it increases the capacitance. Because this is an equation I didn't give you, but I implied it, I guess. I said it, but I'm going to give it to you now. Capacitance without a dielectric and capacitance with a dielectric are related. They're just related by the dielectric constant. So if you take the kappa value and multiply by the capacitance without a dielectric, you get the capacitance with the dielectric. Yeah, I mean, I didn't give you that equation because I thought it was obvious, but somebody asked me about it, so I'm giving it to you now to make sure that it's there.
So is that on the quiz?
No.
Really quick, can you write that constant on the board, the 8 point?
Yeah, you don't have to memorize it, but epsilon naught.
Yeah, thank you. And then for dielectrics, still give us the value on the board.
Yeah, you'd look it up.
Unless
It's either on a table or you'd look it up.
okay.
Yes, 1, 2.
So it's the kappa times the capacitor without the dielectric equals the capacitor with the dielectric?
So look at it like this. If that's confusing to you at all, don't worry about it so much. That is built into this. They're kind of the same equation. If you don't have a dielectric, if it's just empty space or if it's air, this is 1, and that's just not there at all. And this is the capacitance. If you add a different dielectric, then you have the kappa in here. You multiply the kappa times the thing you had before. It's the same thing, kappa times the thing you had before. Right? Same thing. No different. Go ahead.
That was my question.
Oh, good. Awesome.
Are we gonna use this, like, that equation in a problem?
I don't think you need it. That's why I didn't talk about it last
It's
time.
kind of like an extra thing.
Yeah.
Okay,
Somebody asked me about it.
okay.
I wanted to make sure you knew. It might have been in my lab. It might have been the physics 202 class, not this.
Did you
but-
get us confused?
I'm not confusing you. Somebody asked me a question, and I'm like, oh, that's an interesting question. I didn't talk about that in my class. I better talk about it in my class. All right. Last but not least, vectors and scalars, not last. Second to last, but also not least. 1 second, and I get you. Vectors and scalars. The reason we're learning about potential in the first place, like a lot of times people might not say it out loud, but they think, what the heck, why am I learning this? Well, electric fields and electric forces are vectors, and they can be pretty complex, especially in 2 or 3 dimensions when you have to deal with the trigonometry of them and figuring out the components of them. You know that, and I'm gonna make you do that again when the test comes around. But this is kind of a shortcut way to get those answers using scalars, where you can just add them up. You don't have to worry about directions. So electric potential, voltage, is a scalar quantity. Volts are scalars, as opposed to forces and newtons per coulomb, which is the electric field. Those are vector quantities, and they get a little bit more complex.
I was just gonna say, what is that CO? CO? Like, what is that?
Capacitance and capacitance with initial, without a dielectric.
That's not.
I don't know what this, it's just the capacitance with the dielectric and capacitance without.
Okay.
I don't know if there's a special name for it. Your book might have a special name, I don't remember. I don't give it a special name, it doesn't really need one. Capacitance with, capacitance without. Now, last but not least, the thing we talked about last time and that we are going to talk about a bit more today, series and parallel. You talked about it in lab yesterday, I know. He told me. He said you guys covered that a lot. So that's good, I was glad. The capacitors by themselves, fairly easy to do. We just have these 2 equations. When you have more than one, they can be organized 2 different ways. Either they're in a row or they're next to each other. And that's for as many as you want. Notice these 2 equations down here at the bottom. They have this little ellipses at the end. That's because you can add as many as you want. For a parallel set of capacitors, you just add up the capacitance of the individual capacitors. So if I have 2 of them, it's C1 plus C2. If I have 3 of them, it's C1 plus C2 plus C3. If I have 10 of them, it's C1 plus C2 plus C3 all the way through C10. You just add them up. Same thing for a series of capacitors. Same kind of deal, except the capacitance, it's going to go down when I add them in series, when I put them in a row. And we talked about why that was in class. The overall capacitance will be less than the smallest one, and you can figure out how much it is with 1 over CS equals 1 over C1 plus 1 over C2, and on for all the ones that you have in a row. And that's kind of where we left off last class. I wanted to do a couple example problems with that, and then I wanted to go through the homework problems. The ones that we have that we haven't gone over yet, where you have some of each. In some of the homework problems, you have both series and parallel mushed together, and we don't know how to deal with that yet. But there's good news. You do have all the tools you need. We don't need anything else. There's nothing new that you're going to get. It's just application of the stuff that you have. Now, this is a point in space near 2 charges. If I was to ask you, what is the potential at that spot? What is V, electric potential at that spot? If I know the charge and I know the distance, I know the charge and I know the distance, how would I find the potential at that spot? So I could do V1 is K Q1 over R1. How would I find V2? Same thing, right? Except V equals K Q2 over R2. Now, how would I find the total potential at that spot? Just add them up. Does it matter where that spot is? No, just I need to know the distances, I need to know the charges. If I know the distances and the charges, I've put them into my two equations, I add them up at the end. Not too bad. Onward. Do you need more time? I see people still writing. Do I need to go back?
Yes.
Yes. Negative and positive is important. It does not tell direction, it just tells your relative size. So yeah, Q2 I labeled as negative. It would go into this equation as whatever negative number it is. If it was like over here, it would be R1 and R2. If it was down here, it would be R1 and R2. If it was here, it would be R1 and R2. Those would be values you'd either know or figure out.
So the only time you take the absolute values for the
Yeah, because we deal with the direction. The negatives and positives are just about the direction, and we deal with that conceptually. This doesn't have direction, so we don't need the absolute value. All right, let's say I gave you this information. I give you the area of a plate of a capacitor, I give you the distance between them, and I tell you that there's air in between them. You know that the dielectric constant for air is 1. How would you go about finding the capacitance of this capacitor? Say it loud, loud and proud. C equals kappa epsilon 0. Yeah, kappa in this case is 1, but it could be something else. If I told you it was like porcelain or germanium or something like that, you could look it up, you could find it. You look it up, I would give that to you on the quiz in a table. Epsilon naught, constant, also given. A, given in the problem. D, given in the problem. Plug in. Go ahead, and then carry your next.
I just know it's wrong.
Yeah, you have to use the numbers they give you. That's a good point. Sorry, go ahead. Yeah, underneath the problem, there's a link to the book. In the book, there's a table. Use the ones that they give you in the table. A couple people had the same issue. Whatever the dielectric was that they gave had a different value, or it gave them a range, and they picked one out of the middle. So just find the one in the table in the book, because that's the value they give you.
Why are there so many different values?
I don't know. I don't know why they're getting different numbers. It's experimentally gained. They find this through experiment in a lab. So maybe there's different purities of the substances, different isotopes if it's an element, or different combinations or alloys or whatever it might be. Alloys doesn't work because that's metal, but different purities, that does work. So that would affect it. So this is why you test your electronic components if you're an electrician, or you're building circuits, or it's really important to know these values precisely so you measure them.
This might be a dumb question, but I keep getting these wrong on the homework and I can't figure out why. And are we supposed to be, like, say A was 2, are we supposed to be squaring that in the equation, or?
No, if you're given A, if you're given an area in meters squared, you don't square it again because it's not squared in the equation.
So,
Just the units.
yeah, I think I might be messing up the unit conversion stuff.
Possibly. Remember, this is from Physics 1. A square meter is not 100 square centimeters. It's 10,000 square centimeters because it's 100 by 100. 1 meter by 1 meter is 100 centimeters by 100 centimeters. And that's 10,000 square centimeters. So that's a tricky conversion. So if they gave it to you in square centimeters or some other value, then double check your conversion.
Okay.
Yep. I may at some point make you do that. I don't think I'm making you do it today. All right. What do we have here? What we have here is a failure to communicate. That's from a movie. It's a famous quote. Cool Hand Luke, I think, is the movie.
He doesn't have sci fi.
It's not. It's a prison movie, I think.
Yes, it sounds bad.
There was a real question, though. I'm actually asking you here. What is this? You could say it's a circuit, but be more specific. It does have capacitors, and it also has
Battery.
a battery. It's not the best drawing, but you can figure it out, right? Like you can see that there's two capacitors there. You can see there's a battery over there on the right. The battery is labeled with a given amount of voltage. There's a potential difference of 4 volts between the negative and the positive terminals. We also have 2 capacitors in there. You can tell because they're labeled as C1 and C2. C2 is 8 microfarads, C1 is 2 microfarads as we work right to left. How are those connected to each other? What type of circuit? They're in parallel with each other. What does that immediately tell you about them? If I want to find the overall capacitance of the 2 capacitors, C1, 2, for that parallel set, in order to find the overall capacitance, you just add them up. So what would the overall capacitance be? 10 microfarads. If the problem asks you to convert it, you have to make sure you're getting the right unit in your homework problems, right? Like you have to make sure you pay attention to that. If it's on the quiz and I don't specifically ask it, it doesn't really matter. If you do have to convert it, micro is 10 to the minus 6.
This is kind of redundant, but like we could just add it up in microfarads and at the end just do 10 to the minus 6 to just convert it.
Yes,
Okay.
that's correct. As long as the units are the same, you can add them together. All right, but we're not done yet because it asks for 4 more things. What are those 4 things? The voltage and the charge on each capacitor. How might we go about finding that? Yeah, I'm going to write that up there at the top so I have it as a reference. C equals Q over V. I know C equals Q over V. I know C. Is there anything else that I know because I know they're in parallel with each other? Did you say it? Who said it? Somebody said it. Oh, you throw in your voice. It sounded like that came from up here. Say it loud. What do you know? How do you know the V? That's right. They're parallel, so they both have 4 volts across them. Now, if there was other stuff, if there was another capacitor here, which we're going to talk about here in about 5 minutes, I hope. If not, I'll make a video that explains it because we're taking a little longer than I thought. That's fine. I want to get detail. I want to answer the questions. If I don't get to the combination circuits, I'll make a video and make sure it's shared out by the end of the day today because you need it to do your homework problems. Okay, so we know V. V1 and V2 are both 4 volts. Now that we know V for both of them, what else can we find? We know V, we know C. We can find Q. How do we find Q? Say it. Yep. Since C equals Q over V, Q equals CV. Take C times V. 4 times are 2 microfarads. Oh, if we're in micro, this is your question, right? You asked me this same exact question. If we're in microfarads and we don't switch it, that 10 to the minus 6 has to carry through, right? That 10 to the minus 6 is there. It's actually in farads. We want it in base units. We're going to end up with 10 to the minus 6 in our answer too, right? So what do we get? So 2 microfarads times 4 volts, 8 microcoulombs. And 4 times 8, 24 micro. Q equals C times V.
Isn't 4 times 8 equal to 2?
Yeah, like I said. You can't expect me to go fast and do it, right?
It's fine.
So, Dr. Tree did this problem, so he did one where it's like a video of 12 and 12. Like 12 coulombs and 12 coulombs of both capacitors. Then you add them together to make the whole charge circuit.
Oh, okay.
So does that mean you just add the 8 and the
Well,
24?
All right, let me say it this way, and I think I'm saying the same thing that you're asking. If I took these 2 out and I put in a 10 microfarad capacitor instead, it would do the exact same job. There would be nothing about that circuit that would be different that you could detect at all. So that 10 microfarad capacitor, we say, is the equivalent capacitance for this set, for the 2 of them. So what would go on that 10 microfarad capacitor? Well, it would be 10 times 4, 40 microcoulombs of charge, right? So what do we have here? We have 8 and 32, which gives us 40 microcoulombs. It adds up. You could look at it either way. Those are both awesome ways to understand it.
If those are in series, oh, never mind.
If those are in series, funny you should ask, how do we solve this problem?
1 over.
Oh man, that's right.
Plus.
You're on fire
I
today.
know, I understand this from once.
Yeah, you're on fire, so we're frying. Friday. So you're right, 1 over the equivalent equals 1 over C1 plus 1 over C2. So to find the equivalent, I use 1 over C12 equals 1 over C1 plus 1 over C2. 1 over 2 plus 1 over 8. 1 over 2 is the same as 4 over 8. It's 5 over 8. 8 over 5. I don't want to do that in my head, so I'm going to let you guys do that with a calculator. You could do it in your head. I know you could, but you don't have to. You have a calculator right in front of you. What is it? 32 seems not right. Is it 1 over 32? It should be smaller than 2. That wasn't me calling you out. That's me trying to make sense of it. Let's see it.
I did.
Oh, you're a step ahead of me. You went too far. You took the equivalent and
Is that not right though?
it should be whatever 8 over 5 is.
Oh,
Yeah, you just went, yeah, you went too far.
okay. Well,
You went a step too far. That's what I'm saying. Like,
okay.
yeah, you didn't need to keep going. 1 over 2 plus 1 over 8, and then take 1 over that answer, and what do you get? Which is 1.6. 1.6 microfarads is the equivalent. If I took those two out of the circuit entirely and I put a 1.6 microfarad capacitor in the circuit, it wouldn't change a thing. You wouldn't be able to tell the difference. It's the equivalent. They are the same. So we know some things here. This one's a little bit trickier, but not much. As soon as I give you the tools, it's no trickier at all. We know that Q1 and Q2 are the same because of how they charge up. As it turns out, very conveniently, Q1 and Q2 are equal to each other, and they're also equal to what the equivalent capacitance would be. If I just put, because remember, it makes no difference. It doesn't change it at all if I put a 1.6 microfarad capacitor instead of these two, and that 1.6 would charge up with C equals Q over V. I know the voltage that would go across this 1.6, and I know the capacitance is 1.6, so I can figure out the charge on it. And the charge on this equivalent would be the same as the charge on 1, which is the same as the charge on 2. So to find Q12 is going to be C12 times V that's attached to it, which is 4 volts. What is C12, 1.6, times 4? 6.4, so 6.4 microcoulombs. All right, to wrap it up, just to finish, we're almost done. The last thing I'm asking you to do is the voltage. If I know C, and I know V, if I know C and I know Q, I can find V. C equals Q over V. That means V is Q divided by C. Q is 6.4 microfarads, or microcoulombs. God, I'm trying to hurry, I'm doing it wrong. Q is 6.4 microcoulombs divided by C, which is 2 microfarads. The micros cancel out, the 10 to the minus 6s cancel out in that equation, which gives us a base unit again, volts. And what do we get? And do the same thing, but now we're dividing by 8. I know what the answer is going to be already because I also know that the total voltage across them has to add up to the voltage across this. So it's going to be 0.8, but double check me, is it? Isn't that nice? Love it when the math works. All right, let's get started. We got a quiz to take.